Hello viewers, welcome. In this lesson, we are going to deal with the mechanical energy. Now, when we take a gravitational system, usually we have two forms of energy prevalent. Now, these two forms of energy prevalent are the gravitational potential energy and of course the kinetic energy. Now, the gravitational potential energy is the energy possessed by an object as a result of its position with respect to a certain reference point or a datum. Now, let's assume we have a mango fruit hanging on a tree. It is, of course, at a certain height above the ground, if the ground is our reference point. If this mango fruit is let go, it is going to fall under the force of gravity, accelerating constantly at 9.82 meters per second square. All right. So the gravitational potential energy is the energy possessed by an object as a result of its position above the ground. If it lets go, it's going to fall to the ground, being pulled by the force of gravity, and it's going to accelerate constantly with the acceleration due to gravity. All right. Now, the kinetic energy. The kinetic energy is the energy possessed by an object as a result of the fact that the object is in motion. So when an object is in motion, the energy it possesses as a result of it being in motion is called kinetic energy. So if a fruit, as we spoke earlier on in the case of that mango fruit, if a fruit is let go and is falling down, it's going to have gravitational potential energy, of course, and it's going to also have the kinetic energy. Now, these two forms of energy collectively are what we refer to as the mechanical energy. So in a gravitational system, as the one we just spoke about, a system which is operating with, of course, the force of gravity being an actor or a factor within the system, then we are going to have the mechanical energy being constant throughout the system. Okay, so with this simplified diagram, let us try to go through and then get some few points a little bit clearer. Now, assuming we have an object like a ball at a certain height above our reference point. Now, let's assume that our reference point is the ground. Now, this object is going to have gravitational potential energy. If it is let go, it is going to fall to the ground, being pulled by the force of gravity. So this is a gravitational system. Now, at the highest point, when the object is static, motionless, is not moving, its kinetic energy is going to be zero because the object is not moving. An object that is static, motionless, is not going to have any kinetic energy at all. Therefore, the potential energy there is going to be maximum. So you are going to have maximum gravitational potential energy at the highest point when the object is static and motionless. Now, if this object is let go, is coming to fall to the ground, of course, it is going to accelerate with acceleration due to gravity, and of course, being pulled by the force of gravity, gradually coming to hit the ground. Now, just before it hits the ground, when the height is almost negligible, almost zero, we can say the gravitational potential energy is at its minimum, or loosely say it's equal to zero. I said loosely, I'll be coming to why I said loosely equal to zero. Of course, so we can say the kinetic energy is going to be the maximum. Why? Because we are going to have the most highest velocity with which the object is traveling just before it hits the ground. And of course, because the velocity is going to be very high, or the highest at that point, it's going to give us the highest kinetic energy or the maximum kinetic energy at that point. And we can say the gravitational potential energy at that point is almost zero. Almost zero, yes, or at its minimum. I said almost zero because, you see, if an object is on the ground, loosely we say it is having a potential energy or a gravitational potential energy of zero. But is that truly the fact? Because if an object is on the ground, you see certain parts of the object are not actually on the ground. If the bottom part of the object is in contact with the ground and we see all the particles or atoms or molecules there are in contact with the ground and therefore they have a gravitational potential energy of zero, what about those parts of the object that are a little bit high above the ground? So it is going to have its minimum gravitational potential energy because it's on the ground. But to say it is completely zero will be kind of misleading, you know. All right. That's just by the way. So back to our simplified diagram. Now this object that we have is at a certain height. Now the height we have assumed here is 60 meters above the ground. All right. So it is going to have gravitational potential energy as a result of this height of 60 meters above the ground. So now let us determine the gravitational potential energy at that point. So our gravitational potential energy at that point is the mass of our ball multiplied by gravitational acceleration multiplied by the height. So the mass of the ball is 5 kilograms, gravitational acceleration 9.8 meters per second squared, and the height of the object is 60 meters. All right, I hope we have that. So we have 2,940 joules. Now this is the gravitational potential energy of our ball at its maximum point. So we can say gravitational potential energy maximum, right? Maximum. In this case, our kinetic energy is equal to 0. So our kinetic energy is 0. When the gravitational potential energy is maximum, our kinetic energy is 0. Now remember, earlier on we said that at any point in the system, the sum of the gravitational potential energy and the kinetic energy is equal to the mechanical energy. Now, in this instance here, the kinetic energy is 0. So it follows that the gravitational potential energy is equal to the mechanical energy. All goes to the mechanical energy because the kinetic energy is 0. All right. Now, let's assume the object has fallen a certain height. It has fallen down such that its height above the ground is now 40 meters. Its height above the ground is 40 meters. So it has fallen from point A to point B. And its height above the ground is 40 meters. Now there's going to be a reduction in its gravitational potential energy. Why? Because the height has reduced from the object to its reference point, which is the ground. The height, which used to be 60, is now 40. So the height has reduced. So what is going to be the gravitational potential energy at a height of 40 meters above the ground? Okay, so gravitational potential energy at that height, of course, the mass of object multiplied by gravitational acceleration and then the height. So our mass is 5 kilograms, gravitational acceleration, which is constant, 9.8 meters per second square, as we have assumed over here, and then our height of 40. I hope we are getting this. So here what we have? We are going to have the mass multiplied by gravitational acceleration multiplied by the height of the object above the ground. All right? Okay. So here we have 1,960 joules. All right? So this is the gravitational potential energy at point B. The gravitational potential energy at point A is what we have as 2,940 joules. The gravitational potential energy at point B is what we have as 1,960 joules. So we can see that there is a reduction. There's a significant reduction there. Why? Because the height has reduced. Therefore, the gravitational potential energy has reduced. So if the gravitational potential energy has reduced, what is the rest of the energy? The rest of the energy is what has been converted into the kinetic energy. It's what has been converted into the kinetic energy. So unlike at our starting point, when the object was static and kinetic energy is 0, at point B, kinetic energy is no longer going to be equal to 0. Why? Because the object is in motion. Okay, so now let us determine the kinetic energy at point B. The mechanical energy is the gravitational potential energy added to the kinetic energy. This we have said earlier on. So our kinetic energy here, we can say this implies our kinetic energy is our mechanical energy minus our gravitational potential energy. I think that is that. So our mechanical energy here is 2,940. Why is it 2,940? It is because at the starting position when the object was motionless, there was no kinetic energy. It is 0. So the mechanical energy is equal to the gravitational potential energy. directly. So 2,940 is our mechanical energy. So our mechanical energy 2,940 minus our gravitational potential energy at point B, which is 1,960 joules. 1,960 joules. I hope we are getting this point. All right. So the kinetic energy that we have at point B is going to be equal to the mechanical energy in the whole system minus the gravitational potential energy at that particular point, because the two should always be equal to the mechanical energy. So we have 2,940 minus 1,960, and then that will give us 980 joules. So we have 980 joules. So this is the kinetic energy at point B. This is the kinetic energy at point B. So when we add this kinetic energy at point B plus the gravitational potential energy at point B, that should give us the whole mechanical energy in the system, which is 2,940. All right? Okay. So now that we've been able to find our kinetic energy at point B, we should be able to find or calculate the velocity of that moving object. Now the object is in motion, so it has kinetic energy. And any object that has kinetic energy, of course, has a velocity. It has a velocity or it has speed, depending on whether we are taking direction into consideration or not. In this case, the object is falling with respect to a certain datum in a particular direction, so it has velocity. So the velocity, we can determine the velocity. So our kinetic energy, K, is our half mv squared. So our v is equal to the square root of 2 times the kinetic energy all over the mass. So our velocity is 2 times the kinetic energy. The kinetic energy is 980 joules. So we have 980 joules all over the mass. Now the mass of our object is 5 kilograms. As you can see over here, it's 5 kilograms. That's the mass of the object. So we put our 5 kilograms in there, and our velocity now becomes 19.8 meters per second. So this is the velocity of the object, 19.8 meters per second. That is the velocity of the object at point B. At point B. Now, in case we should consider any other point, if we should have any other point, like we should have a point C, a point D, always at that particular point, the gravitational potential energy at that point added to the kinetic energy at that point should be equal to the mechanical energy in the system. And we said the mechanical energy in the system is 2,940 joules. So at maximum here, what we have is maximum gravitational potential energy. Gravitational kinetic energy is 0. Just before the object hits the ground, we say we are going to have maximum kinetic energy, and then gravitational potential energy at there is almost equal to 0. All right? Okay. So when the object is now falling, the gravitational potential energy is reducing and the kinetic energy increasing. Just before it hits the ground, the kinetic energy is now maximum, and then the gravitational potential energy is at its minimum. It's at its minimum. So the whole situation reverses. The whole situation reverses. So now this is the velocity of our object, 19.8 meters per second at point B. At point B. Now, let us find the time. As the object is falling, it is falling from point A to point B. Of course, it is consuming time. If an object is in motion, time is, of course, elapsing. Time is being consumed by the object as it is undergoing its motion. So now let us find the time. Our acceleration is final velocity minus initial velocity divided by the time. So acceleration, final velocity minus initial velocity, all divided by the time. Now we are looking to calculate our time. We are looking to find the time. So our time t is going to be final velocity minus initial velocity all over acceleration, right? So our final velocity, what is our final velocity? The velocity that we have at point B. The object started from point A. It's now at point B. Its starting position is point A. That is our initial velocity, u. Its final destination with respect to our situation here is point B. So the velocity there is v. So the velocity at v minus the velocity at what? A. All divided by the acceleration with which the object is actually moving. So our velocity there, 19.8 meters per second, minus 0 meters per second all over our acceleration, which is 9.8 meters per second square. So we have 9.8 meters per second square. So what do we get over there? What does that gives us? That gives us 2.02 seconds. So we have 2.02 seconds. So now this is the time that we have, 2.02 seconds. Now that is the time consumed by the object in falling from point A to point B. The time consumed by the object in falling from point A to point B is 2.02 seconds. Okay? Alright. Now it has covered some distance. The object has covered some distance. Now the distance it has covered, of course, from the diagram, we can clearly verify that is 20 meters. Because it used to be at a height of 60 meters above the ground. Now it is at a certain height of 40 above the ground. Taking the 40 from the 60, we are going to be left with 20. Now we can verify that and see whether that is actually the case. So our distance is ut plus half at squared. Now what do we have here? Initial velocity of 0 times 2.02 plus half acceleration 9.8 and our time 2.02 squared. Now this gives us 20 meters. So we verify. Or alternatively, we can say our distance is final velocity squared minus initial velocity squared all over 2a, 2 times the acceleration, right? So s equals v squared 19.8 squared, u squared is 0 squared, 2 times 9.8. Now what do we have here? This will give us 20 meters. And that is the distance that the object has fallen from point A to point B. Alright, so here we are looking at a gravitational system. A gravitational system because the whole system is working with direct correlation or under the influence of the force of gravity. The object is falling under the force of gravity. So of course it's being pulled by gravity, and it has some potential energy, it has some kinetic energy. So the potential energy is gravitational potential energy, and then the kinetic energy. Put together, that gives us the mechanical energy. At any particular point in the system, the mechanical energy is a constant. So if the gravitational potential energy changes at a point, of course, the kinetic energy will equally change, such that the two added will always give us a constant mechanical energy in the system. So as we said earlier, at point A, Ke is 0, so the whole mechanical energy in the system is equal to the potential energy. So the mechanical energy in the system is equal to the gravitational potential energy in the system when K is 0. Now just before it hits the ground, we can say that our gravitational potential energy is at its minimum, or let's say it's almost equal to 0 or 0. Therefore, the kinetic energy is equal to the mechanical energy at that point. So the whole system keeps on reversing as we move in either direction. When this is increasing downwards, the other will be reducing. When the other is reducing upwards, the other will be increasing. So downwards, gravitational potential energy reduces, kinetic energy increases. When we are going upwards, kinetic energy reduces, and then gravitational potential energy increases. Alright, so this brings us to this lesson on mechanical energy, where we've seen gravitational potential energy and kinetic energy, and how to do some simple computations or calculations with respect to these two. So I think all is said and done for this particular video. Okay, so let's keep learning, because learning is fun. I'll see you in my next video.